Hey there, ever stop and think about what's actually stopping you from just falling right through your chair? It's this incredible invisible glue that holds literally everything in the universe together. And today, we're going to zoom way in and figure out how it works. Let's do it.
No, really, think about it for a sec. You've got a grain of salt, right? Why doesn't it just crumble into a cloud of individual atoms? Or how does a single drop of water manage to hold its shape? Well, it all boils down to these fundamental rules that tell the tiniest bits of matter how to behave around each other.
All right, so here's the game plan. First, we'll meet the two main types of this glue. Then, we'll dive into the forces inside molecules and the ones between them. After that, we'll see how all this tiny stuff shapes the big world around us. And then we'll wrap it all up with the one big idea you need to remember.
Okay, so to really get a handle on this, let's think of it like we have two totally different kinds of glue. You've got your super glue, right? The really permanent, strong stuff. And then you've got the glue on a sticky note. It works, but it's much weaker. Both are super important. They just do completely different jobs.
So, let's meet our two main players. First up, you have chemical bonds. This is our superglue, the strong stuff that holds individual atoms together to build a molecule in the first place. Then, you have intermolecular forces. This is our sticky note glue, the weaker stuff that just gets whole, separate molecules to, hang out with each other.
All right, let's dive into that strong glue first. We're talking about the superglue here. We're zooming right into the molecule to see these powerful connections that literally define what a substance is. This is where atoms make those forever and ever commitments to each other.
But wait, why do atoms even care about bonding? Well, it's all about feeling stable and complete, kind of like us, right? See, most atoms are trying to be like the noble gases, the super chill, unreactive elements on the far right of the periodic table. They have a full outer shell of 8 electrons, and that's the dream. This ambition is called the octet rule, and it's the why behind pretty much everything that follows.
So, one way atoms can hit that magic number of 8 is, well, it's basically a heist. You've got a metal, like sodium, which has one extra electron it's dying to get rid of, and then you have a non-metal, like chlorine, which is just one electron short of a full set. So sodium just gives its electron away, and chlorine gobbles it up. Now sodium's positive, chlorine's negative, and bam, opposites attract. That intense attraction is an ionic bond, and it's what makes table salt so tough.
But it's not always so dramatic, not always a big heist. Sometimes atoms, especially when they're both nonmetals, decide to be more cooperative. They share electrons to get to that stable state. It's a team effort. They can share one pair of electrons, which we call a single bond. Or they can share 2 pairs for a double bond. And if they're really committed, they'll share 3 pairs, forming an incredibly strong triple bond.
Okay, so we've used our superglue to build the molecules themselves. Now it's time to zoom back out and talk about the sticky note glue. These are the weaker forces that decide how all those molecules we just built are going to interact with each other. It's kind of like their social life, And when we say weaker, we are not kidding. The difference in strength is absolutely massive. Get this. It can take over 25 times more energy to break the strong bond inside just one of these molecules than it takes to just pull 2 of those molecules apart from each other. It's not even in the same league. We're talking about a huge difference in power.
So let's start with the weakest of the weak. These are called London dispersion forces. Now, picture this. Electrons are constantly whizzing around inside a molecule, right? For just a split second, more of them might be on one side than the other. This creates a tiny, temporary, lopsided charge, which can then attract a neighbor. It's super brief, like a fleeting handshake. But the key thing is, every single molecule does this.
Okay, now let's step it up a notch. Some molecules aren't just temporarily lopsided, they are permanently lopsided. They have a built-in positive end and a negative end. We call these polar molecules. And because of this, they create something called a dipole-dipole force. The positive end of one molecule is always attracted to the negative end of another. It's a much more consistent, reliable attraction than that quick little handshake we just talked about. And now for the superstar of the weak forces, the VIP, the hydrogen bond. Now, first things first, don't let that name bond fool you. It's not a real strong superglue bond. Think of it more as a superpowered, extra strong version of that dipole-dipole attraction. And this one? Oh, it is unbelievably important for life.
So what's the secret? There's a golden rule here. For a hydrogen bond to form, hydrogen has to be bonded to one of only 3 elements: fluorine, oxygen, or nitrogen. Just remember,
F-O-N, like fun. The perfect example, of course, is water, H2O. The hydrogen is bonded to oxygen. And these super strong attractions between water molecules are the entire reason water is so weird and wonderful. It's why it has such a high boiling point for something so small.
All right, so we've got strong glue, weak glue, octet rules. You might be thinking, so what? Well, this is the payoff. This is where we connect all that tiny, invisible stuff to the real physical world that you and I live in every single day.
Just take a look. On one hand, you've got salt. It's held together by those super strong ionic bonds. You need a ton of heat, a ton of energy to melt it. That's why it's a solid with a crazy high melting point. But then you have something like candle wax. The molecules themselves are strong, but they're only attached to each other by those weak sticky note forces. It takes almost no energy to melt wax. See? The type of glue at the microscopic level directly decides what you see at the macroscopic level.
And this whole idea even explains something as simple as mixing drinks. There's a simple chemistry mantra, like dissolves like. It just means things with similar forces mix well. Polar things, like salt, dissolve great in other polar things, like water. Their forces are compatible. But oil? Oil is non-polar. Its forces are totally different from water's. So when you try to mix them, they just don't. They can't find a way to happily interact. Okay, let's wrap this all up. It's time to nail down the one big takeaway, the fundamental difference that really explains, well, pretty much everything we've been talking about. Okay, here it is, the bottom line. The strong glue, the chemical bonds, that's what holds atoms together to make the molecule. This defines the substance's chemical identity. It's why H2O is water. But the weak glue, the intermolecular forces, that's what holds whole molecules next to each other. And this is what determines the physical properties, like boiling point, melting point, whether that water is solid ice, liquid water, or gaseous steam.
So, I'll leave you with this final question to chew on. Next time you're boiling a pot of water for pasta, think about what's really happening. Are you actually breaking the strong bonds inside the H2O molecules and turning them back into hydrogen and oxygen gas? Or are you just adding enough energy to break the weak connections between those water molecules so they can escape and fly off as steam? If you can answer that, then you've truly understood the universe's hidden glue.